Hello everyone. We are going to continue our class of foundation engineering. We are still on the chapter number 2, and today's video will be about dilatometer test, the point number 8 of this program. Okay, so as usual, we are going to discuss how the test is performed and what kind of soil parameters we can obtain from this test. Okay, so let's go. What is the test about? Dilatometer test. If you see this DMT, it means dilatometer test. Okay, so this test, the use of this test, it's using like flat plate, which is invented by the first person who invented it is the Italian guy, Marchetti. I'm not sure if I'm reading his name very well. Marchetti. Okay, and this is apparatus. This is actually the dilatometer. Okay, and these are the equipment going with it. Okay, this is, for example, gas inside, the source of our pressure. It is the same as the pressure meter test, but here, instead of pressure meter, we are using dilatometer test, dilatometer apparatus. This device, okay, will be inserted in the ground, and by using the pressure, okay, we will press and we will do some measurement. Technically, this is how it works. So this dilatometer test can be connected to road like this. Okay, you can see like cone penetration road, and can be pushed into the ground. Right? You can see this cable here, same as here. And the equipment is the dimension are like this 220 millimeters length, means the length of this. Okay, and the width like this is about 95 millimeter, and the thickness is about 14 millimeters. Okay, you can see these dimensions here. This length, okay, to about 22 centimeters. Okay, and the width is 9.5 centimeters. Okay, the thickness here, the thickness of the blade, it is like that. If I present this is the face, and this, if you turn it, you can see this side, and it allow you to judge on the thickness. Okay, so the thickness is 1.4 centimeters. All right, so this thin flat circular, can you see this? This is a steel membrane. This steel membrane is expandable. Okay, and this is actually the one that making the measurement. Okay, the blade will just be used to insert the membrane into the ground, and the membrane will do the measurement. Okay, so this membrane has like a diameter, okay, because it's circular, diameter of 6 centimeter, 60 millimeter. You can see it here. Okay, 60 millimeter. So it located only at the center of one side. Okay, it means the other side there is nothing. And you can see another one here. So it means you can change it. You can fix it here. Okay, you can see here, it can be fixed but only one side of the gelatometer. Okay. So let's keep this here. So how does it work exactly? How does it work? The probe, this gelatometer, is inserted into the ground with same cone penetrometer testing rate. Okay, you can see here. Same, we just push. The only thing that will change, the head is changing. Okay, so something like this. We push it into the ground and gas, this, you can see this bottle, nitrogen, it can be nitrogen gas. Okay, these are the to measure the pressure and also the to record. You can see the PC that is recording. Everything is connected to this until the dilatometer, okay, into the blade. So if now you reach the depths you need, the required depths, then high pressure nitrogen gas, this gas in this bottle, is used to inflate the membrane, this membrane, only this one, okay? So as you can see, the schematic view is here. And this view is kind of like this one, same, okay? This side, the side view, okay? And you push and inflate the membrane, this membrane only. Can you see? This boss, this this part is when the membrane is inflated. Something like this. Okay. So then we measure two pressure, as you can see here. This pressure and this pressure. Okay. This pressure A is the pressure required to lift off the membrane. Okay. Because you have to push and reach a minimum limit before the membrane start reacting. Okay, to lift off the membrane. You can see here, okay, this is the P0 we obtain. And pressure B, which is here, is the pressure at which the membrane expands 1.1 millimeter into the surrounding soil. And you see here, 1.1 millimeter, okay? The membrane expands 1.1 millimeters. So don't be surprised that to see somewhere P1 here and P2 here, this is just nomination. It doesn't matter. Just remember that the first pressure is just the pressure to lift off the membrane. The second pressure is the pressure corresponding to the expansion of the membrane to 1.1 millimeter. Okay. So how will you then use these two pressures, P1, P0 and P1? Because this is the only thing you need. This is the data you will obtain from the dilatometer test. Okay. These are two data you will obtain. So how will you use them? The pressure, the reading A and B. A, remember A is P0 and B is P1, okay? These are corrected using this. P0 is contact pressure, P0, and you can use this formula to correct them. And expansion stress, P1, okay? You use this formula. What is delta E? Delta A, sorry. Delta A here, okay? And delta B, what are these? Okay, delta A is vacuum pressure required to keep the membrane in contact with it sitting. Okay, delta B, air pressure required inside the membrane to deflect it outward to a center tension of 1.1 millimeter. Okay. The pressure required inside the membrane. And Z, this one, Zm here, and it is here also. This is gauge pressure deviation from zero when vented to atmospheric pressure. Okay, the gauge pressure here. So if you obtain then P0 and P1, how will you use these two, P1 and P0 and P1, to obtain the soil parameters? Okay, please don't forget that A and B are the first measurement you will do here. Okay, this P0 and P1 are just correction of this A and B. Okay, A and B are already explained here. Pressure A, pressure B. What you will measure, pressure A and pressure B. And then you correct this pressure A and pressure B like this. Okay, pressure 0 and pressure 1. Okay, so if you have then P0 and P1, and I said in some books you will see P1 and P2, but it doesn't matter, it's same. Okay, I will put this here. And in normally you conduct this test, the depths apart is 200 to 300 millimeter. It means you measure it. If you measure it at this position, you go deeper to like 200, let's say 20 to 30 centimeters, and you measure again. Okay, so the result of from this, we can obtain 3 parameters from this. Okay, these are the 3 parameters, and as you can see, these parameters are using the P0 and the P1. Okay, the first parameter is material index. Material index is obtained, ID is obtained by using this P1 minus P2. P1 is this one. P0, sorry, P1 minus P0. P1 is this one. P0 is this one. And you divide it by this P0 minus U. Okay, U is pore water pressure. Okay. And you get also the second parameter you can get is the horizontal stress index. And from this one, you can obtain later the K naught. Okay. The K naught, you know the K naught. Okay. K0. We will see it later, which means the ratio of the sigma H, sigma V. The sigma 0 here, prime, is just the vertical stress. The third parameter is dilatometer modulus. From this, you will be able to obtain elastic modulus of your soil later. Okay, so this is obtained using P1 and P0. Okay, P1 minus P0 and factor to 34.7. Okay, dilatometer modulus. You can obtain later the young modulus of the soil from this later. So here is just example of test result from this reference in Bangkok clay. which is a very famous clay, Bangkok clay. Okay. This line, this one is P0. Okay. P0. This is the minimum pressure to take the plate off. P1 is this one. This is the pressure required to expand the plate, the membrane, 1.1 millimeter. Okay. And this ID is this one, material index. Okay. KD. I told you you will be able to obtain K naught from this one later, this formula. Okay. And the modulus, dilatometer modulus. Okay. This one. This is typical result of from dilatometer test. Okay. And from this now, especially from this KD, you will be able to obtain several soil parameters. Okay. Let me put this here. We'll keep them here. We will use them. Okay, especially this one. Okay. The professor Marchetti from Italy, who developed this test, provided this following correlation from the beginning. Okay. K naught, as I was saying, the K naught of soil means the coefficient of earth at rest, okay, can be obtained from this KD, okay, using this formula. K naught, this is the coefficient of earth at rest. And the overconsolidation ratio also can be obtained from this KD, same, okay, overconsolidation ratio, okay. And for a normally consolidated clay, this coefficient, this ratio, the undrained shear strength divided by the effective vertical stress, this ratio is 0.22, okay. But anyway, you can see here, this ratio is right here again for normally consolidated clay. So using this ratio, 0.22, you can replace this by 0.22, okay? You can replace it so that you can obtain easily the undrained shear strength of over consolidated clay using this formula, okay? The undrained shear strength of over consolidated clay using sigma prime 0, okay? And KD again. And this modulus, dilatometer modulus, will help us to obtain the elastic modulus, modulus of elasticity. This one, okay? You can see ED here by using, of course, the Poisson ratio. It's not written here, but I guess you know that this is just Poisson ratio. You can simply guess that, I think. So these are the primary parameters we knew for clay. And next, we have our other relevant correlations, like this reference gave us this correlation. The undrained shear strength can be obtained using this formula, but still using the KD. Okay. And also the soil frictional angle, this reference said we can obtain it from this using this formula or this equation. Or the peak one can be obtained from this. But you can see all of them are using this KD. Okay. And instead of KD, if you want, you can use K naught like this. Because as you know, K naught can be obtained from KD. I will go back to show you that relation. Like here, you can see K naught here. Okay. So this K naught can be used also instead of KD to obtain this. Okay. And this table is showing a relationship between the material index. Material index is this one. Okay. ID. The material index and the dilatometer modulus. What is like if you plot the material index horizontal axis and the vertical axis, the dilatometer modulus, you can guess, okay, what type of soil, what is the soil you are dealing with. Okay. If you are here, means if the ID material index is here to here, for example, okay, 0.6. From here to here, it is like a clay. Here is silt, here is sand. The range are different for each type of soil. And then if you go up, like here is soft to hard. For sand, for silt, compressible to very dense. Okay. There are some transition zones, okay, as you can see here. Silty, okay, like this is silty clay, this zone. Okay, it's still clay, but silty clay. Okay, this is silt, but sandy silt. Okay, or clay silt. Okay, sand. This is silty sand. Okay, but anyway, from loose sand to very rigid sand. Yeah. So if you have your ID, the material index from dilatometer test, and you have the dilatometer modulus, you can guess what kind of soil, what type of soil you are dealing with, and if it is dense or soft or medium, okay, something like that, using this design chart. Okay. So I think that's all for this part of the chapter. We will just stop here. Okay. Thank you very much for your time and see you very soon.